Hello and welcome. So we're going to be talking about the fundamental trigonometric identities today. Now, when we say fundamental, we're going to be doing everything except the cofunction and the even-odd identities. So just the reciprocal, quotient, and Pythagoreans. So first off, let's kind of go over the basic trig stuff. So we have the reciprocal identities. So remember, we have sine, cosine, tangent, right? SOHCAHTOA. Sine is the opposite over hypotenuse, cosine, adjacent, hypotenuse, tangent, opposite over adjacent. Right? And then you have your reciprocal trig functions, which are if sine is opposite over hypotenuse, hypotenuse over opposite is your cosecant function. So it kind of gives way to this little obvious identities where sine is 1 over the value of cosecant. It's essentially just saying flip and you get cosecant, right? Or vice versa. 1 over sine is the cosecant value, right? And then cosine would then be 1 over secant, secant, 1 over cosine. Tangent is 1 over cotangent, cotangent is 1 over tangent, and those are your reciprocal identities. Not too bad, it's just saying that you can always just get the other one by flipping it. That's it, okay? All right, so now let's kind of go off to, for the other two identities, the quotient Pythagoreans, right? Let's go a little bit to a diagram here. So we have the coordinate plane, right? You have the x-axis, you have the y-axis, which makes this the origin over there. And let's say that I have another point on the graph in the first quadrant. I don't know where it is. I'm going to say some x and some y. Well, in order to get to that x value, I have to travel some distance x, right? That literally is the value of x, is however far over I go, which makes the y the however up I go there. So the y value is literally the y value, right? So the coordinate point, the x is the over, y is the up. And just for argument's sake, I'm just going to put a 1 here. It's not going to matter what number you pick here, of which I will guarantee that. 1 is just going to make this easiest and fastest, right? So for that hypotenuse, we're going to use 1. Now, if I try to find, let's say, the sine of my angle theta, notice we have it in that angle closest to the origin, we're going to have the opposite over hypotenuse. Okay, opposite over hypotenuse cosine of theta, we're going to go x over 1 because that'll be adjacent over hypotenuse, right? Which means essentially that your value of sine and your value of cosine is going to essentially be the x and y value of your point here. All right, so what ends up happening is if, let's say I wanted to find the tangent value, is a little more significant, then we have the y over x. Well, the reason why it's significant to have these ones is that we know the y is essentially sine, and the x is essentially cosine. And this is where we get what we call the quotient identities, is that tangent can be written in terms of sine and cosine. It's sine over cosine, right? Cotangent, as our reciprocal identities tell us, is that we can essentially just flip that and we get cotangent. All right, not too bad. Now, following that, we also get our Pythagorean identities pretty quickly. When you hear the term Pythagorean, you probably are thinking Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared in a right triangle, right? And so if we actually try that here, right, where we know sine is the y, cosine is the x, right, then Pythagorean theorem yields that we have leg squared, so sine squared, plus cosine squared, our other leg, squared, equals our hypotenuse, 1 squared. Now, just as a notation heads up, the reason why I'm writing the 2 before the angle is that you can write sines like that, sine squared, but if you write it that way, it looks like theta is what's being squared, not the sine function. So, I mean, if you leave it as parentheses square, that's totally fine, but without that square, it implies that it's on the theta, not on the function, which is why typically in notation you'll see squares before the angle, and that is just kind of a reiteration that the square is not on theta, it's on the sine function itself. You have 2 of those sine functions. All right, that's just a quick 2-second thing. All right, so 1 squared is just 1, right? Sine squared and cosine squared. And that is your first Pythagorean identity. If you do sine squared theta plus cosine squared theta, we get 1. Now, if you were to literally Google Pythagorean identities, you can get anywhere between 1 to like 9 different Pythagorean identities. Everything is going to stem from this, that this is the main Pythagorean identity, sine squared plus cosine squared equals 1. Now, I personally like using 3 different Pythagorean identities, and I'm going to manipulate my current one in order to find the others. So, just for fun, what if I decided to divide by sine squared on every single term, right? Totally valid because you have an equation, right? What you do to one side, you do to the other. You don't get to pick and choose division, so if you do it to one, you do it to all, right? On the furthest left, we get sine squared over sine squared. Same thing over the same thing as 1. Now this is going to be the same thing as cosine over sine squared, like that, right? Having those squares separately is the same thing as having them together. And fun fact, you just happen to know that cosine over sine is the same as cotangent, which means that this is really just another way to write cotangent squared equals, and then for the same reason why this is cotangent squared, right, we just happen to know that 1 over sine is cosecant, which means that when you're looking at 1 over sine squared, that is the same thing as cosecant squared. Right? So then we get a still Pythagorean identity. It came from the original. But it's different enough that I usually count this as a separate Pythagorean identity, right? You have one for sines, cosines, one for cotangent, cosecant, right? And to get the third one, it's actually not too bad either, right? You still have your sine squared plus cosine squared equals 1. And then instead of dividing by sine squared, you can get the third iteration by dividing cosine squared instead. All right, so on the leftmost, sine over cosine, well, sine over cosine is the same thing as tangent, so sine squared over cosine squared is tangent squared, plus cosine squared over cosine squared, that is 1, equals, and then we know that 1 over cosine is the same as secant. So secant squared theta. All right, now this one I am going to slightly rearrange. I'm going to put the 1 first. 1 plus tangent squared equals secant squared. All right, and there you go. Those are what I would consider the 3 Pythagorean identities. Honestly, depending on who you talk to, mathematicians, they'll say that there's only one, sine squared plus cosine squared equals 1. Or if you rearrange these, like if you subtract the 1 to the other side, you get cotangent is cosecant squared minus 1. Some people will call that a different version of the Pythagorean identity, right? But honestly, these are the main 3, and you can rearrange stuff to get the others if you need them. All right, so there you go. To help you remember this, there is a kind of silly acronym. So we have S, and C, and a 1. So the way that I remember this is I think Santa Claus. Wait, is there an E at the end? Whatever, this is recorded, but I don't know how to spell it. It's fine. Is number 1. All right, Santa Claus is number 1. All right, so the way I remember it, so S for sine, C for cosine, right, is your equal sign, and then the number 1, right? So Santa Claus is number 1. Sine squared plus cosine squared is 1. Right? And that's how I remember this first one. The next one, I remember this one. It's also a little silly. I remember as 1 cottage cheese. Right? CSC is kind of hard to get as an abbreviation, is kind of standing for something. But 1 cottage cheese. There you go. Right? And then the last one I remember as 1 tan secretary. Right? 1 tan for tangent, secant, secretary, right? And then as long as you remember that all of those functions, all the trig functions are squared, those are your Pythagoreans. And that's how I remember them. A little silly, but there you go. So kind of using those in action. So we have use the appropriate Pythagorean identity and asking what can this simplify to. The biggest thing to keep in mind here is that these are not equations, they are expressions, meaning that you can't move the one or move the sign or anything else, like you can't do anything with it. So you'd say, all right, well, how on earth does this simplify if I can't move anything? Well, first off, it says use the appropriate Pythagorean identity and say, okay, well, we have three of them we just talked about, right? Which one of them uses sine? That's your Santa Claus is number one, right? So what I would do is I would work off to the side, like not even looking at that problem, right? Sine squared plus cosine squared equals 1, right? And for the Pythagoreans, that theta is a placeholder. It is a placeholder for any angle you want it to be. So for example, our angle is 30 degrees. What you can do is this identity is true if that is 30 degrees right there, right? It would be true if it was 5 degrees. It'd be true if it was 20 pi is a radian angle, right? It can be a lot of things, but as long as the angle for the sine and cosine functions, and those sine cosines are squared, then that sum is always equal to 1, and that's always true for your identity. Okay, so your theta is 30 in this case, you can literally put 30 in its place. All right, so now let's do a substitution. My goal is getting 1 minus sine squared. And I'd say, okay, what does 1 minus sine squared equal with a Pythagorean identity? Well, my goal is 1 minus sine squared, so I need to get my 1. It's there, right? It's alone, but we need to have a sine squared with it, so I'm going to subtract sine squared. All right, and when I do that, left side, same thing, right? Positive, negative, they cancel, so we're left with the cosine squared of 30 degrees equals 1 minus sine squared of 30 degrees. Right? We haven't broken algebra, we're just looking at Pythagorean identities, right? We haven't actually done anything to our problem yet, because now you'll notice the right side of that identity is the expression that we're given. Well, what the heck does that equal? Cosine of 30 degrees. So by the Pythagorean identity, right, that will equal cosine of 30 degrees, cosine squared of 30 degrees. That's your answer, right? So when we say using Pythagorean identity, what can it simplify to? You're essentially going to take the identity, right, do some algebra to it, move it around until we get the exact substitution for your expression and go from there, right? So that's going to be the first example. So another example, let's partition that off. So I'm looking at that and say, all right, well, this one has an angle of alpha. Well, all that means is that we're just going to put alpha instead of theta. It's not even that crazy. Okay, so this one has cosecants and cotangents. Well, that's going to be your one cottage cheese that uses cosecants, cotangents. So off to the side, all right, we have 1 cotangent squared equals cosecant squared. And I'm just putting alphas instead of the original thetas because we're working with alphas. Right? As long as you're consistent, you're good to go. Now this one is cosecant minus cotangent, so let's do subtraction of cotangent. All right, that cancels and you get 1 equals cosecant squared minus cotangent squared. All right. So it's all right. Well, this is really similar, like cosecant squared minus cotangent squared. That is so close to what we're looking at. The only difference right there is those 4s. So how can I move those 4s, right? We don't have an equation to work with. There's nothing to do with those 4. I can't just magically divide 4, right? Because there's not an other side of the equal sign to work with. And no, you can't just set it to 0 because we don't know if it actually equals 0 or not. So If you don't start with an equal sign, you can't use one. All right, so I'd say, all right, well, how can I change this then if there is no equal sign? Well, there's a particular operation known as factoring. I sometimes consider an operation, it's pretty much your operation for expressions that whenever you need division, right? So GCF, 4, right? They both have a 4 in common, pull it out. And you get cosecant squared minus cotangent squared. Oh my, what a coincidence. It's kind of like you wanted cosecant minus cotangent, right? Now it literally exactly matches, and what's the substitution? What does cosecant squared minus cotangent squared equal? 1. So then you get 4 times 1, which is 4. There's your answer, right? That's what it simplifies to using Pythagorean identities. And that's mostly everything when it comes to Pythagorean identities. Like, use some algebra on here, try to make it look like what you have to work with, and then plug in the substitution. That's it, okay? Now, the second part is working with algebra and trig. We're actually not going to be looking at those identities much. We're just going to be working with the algebra, all right? So first off, let me just ask or go over a few basics. If I have 2x plus x, you get 3x, not 3x squared, just 3x. If this is 2x times x, then you get 2x squared, right? Squares appear when you have multiplication. That's the definition of exponents, right? If I have, let's see, 2x plus y, can those combine? No, because they're not like terms. One has x's, the other is y, right? If it's 2x times y, can we combine those? I mean, technically, right, it's just 2xy. You can just write them all together, but nothing actually combines and changes powers or coefficients, right? There you go. All right. Now, fun fact, how you work with variables is how you work with trig functions in algebra, right? So first off, we have sine plus sine. That's like saying 2x plus x, right? They're both like terms. They're both sines. So then you get 2 sine of theta. When you combine trig functions together, their angles will never change. You only change the quantity, right? Whether the trig function gets squared or whether you're changing the coefficient, but the angles themselves will not change, all right? And then on the tail end of this, we have tangent times tangent. So tangent times tangent is tangent squared, right? And then there's that subtraction from the beginning. So we have 2 sine minus tangent squared. And now we have like the 2x plus y scenario. One's a sine, the other's a tangent. Those can't combine. That's as simplified as it gets. Okay? Now keep in mind it said simplify. It doesn't say factor. Don't try factoring that now. That's simplified. All right? This next one, simplify. If we wanted to simplify this, typically we want to multiply or distribute those parentheses out. So start distributing. We have 2 cosine times cosine. Well, 2 times 1 is 2. Cosine times cosine is cosine squared. 2 cosine times negative 3. Well, 2 times negative 3 is negative 6. And then we have a cosine there, so negative 6 cosine. Negative 1 times cosine, negative cosine. Negative 1 times negative 3, 3. And just like you would with any trinomial with x's and y's, right, you want to combine like terms, right? You have negative 6 and negative 1 cosine. Well, those combine to give you negative 7 cosine. Plus 3 at the end, 2 cosine squared. There you go. Now, again, the instruction said to simplify, not to factor, meaning this is your answer. If you factored it, it would literally put you back to your original. That's not what you want. All right, there you go. Now, this next one does say to factor, right? And sometimes students kind of freak out with this. First off, before you do anything else, what is the first step to factoring? GCF, right? This has a 4 in common. Pull it out. So we get cosine squared x minus 25. Okay, now if you know your factoring identities really well, this is a difference of squares, right? Cosine squared is a perfect square cosine. 25 is the perfect square of 5, right? So when we're looking at that, say, okay, well, if you know difference of squares, you get cosine plus 5 and minus 5, each in a parenthesis, right? But let's say you didn't. Let's say you didn't quite recognize that. Well, that's totally fine. X is already in the problem, so I'm going to use I don't know, W. I'm going to say W is my cosine function. So then we get 4 parentheses W squared minus 25. Hopefully this looks a whole lot more familiar, and you're like, oh yeah, well that's just W times W. That's just 5 times 5. So that's W minus 5 and W plus 5, right? Because it's a difference between them, right? GCF out in front. Fun fact, that works the exact same way with trig functions. You would have the 4, cosine minus 5, and cosine plus 5. Right, your goal is not to solve for x, it was just factor, you're done, you factored it, right? This can't go down anymore because these do not have squares, there's nothing more you could do, even if you wanted. All right, so there you go. All right, so next one, it looks scary, take it in pieces, right? If you want to factor, what's your first step to factoring? GCF, right? We have thing 1, thing 2, thing 3. You have 3 different terms, and we know terms are separated by addition, subtraction, right? That's how we know we have 3 different, right? And if we're looking for GCFs, keep in mind, the theta is not a GCF. Sorry, alpha is not a GCF, right? This just tells you that you have a trig function, right? It's like saying square root of 2, right? The alpha is attached. You couldn't have a square root without a number in it. It wouldn't make any sense. If you have sine without an angle behind it, it doesn't make any sense, right? The alpha is attached to the sine, right? If I move sine, alpha's just going to go with it. Don't do any weird things with your alpha on this one. So it's all right. Between the yellow, the orange, and the blue, what do we have in common? Well, cosine. This has a cosine, that has a cosine, that is a cosine. Pull out a cosine. Now you'll also notice that you also have a number in common as well. There's at least a 2 that goes in all of these. So 2 cosine alpha is something that goes into everything. That's your GCF. So first off, 4, pull out a 2, we get a 2. Now between these, I'm pulling out a cosine, so my sine squared does not change. Right? If I have a cosine and I pull out the cosine, right, those essentially take out the cosine, bring it out front. Next, we have negative 10, pull out the 2, we get 5, right? Again, I'm pulling out the cosine, which means we should have just sine alpha left. All right, the last one, we have negative 6 cosine. If I pull out the cosine, you're left with negative 3 because you're pulling the 2 out from the 6. All right, there you go. There is your GCF pulled, and factoring is looking better. And again, if this does not look familiar, if you stare at this and you're like, what on earth do I do? Don't freak out, right? Maybe put in x's for the sign instead, right? This would be x squared, this would be x. So then you would have 2x squared minus 5x minus 3. And you're like, oh, I can factor that. That looks a lot more familiar. Go with it. Do it. Right? 2 numbers that are going to multiply to negative 6 but combine to 5, that's negative 6 positive 1, right? And remember that because there's that leading coefficient there, you can't go straight to your parentheses, right? Divide by that leading coefficient, negative 6 over 2, negative 3, so x minus 3. Bottoms up method, and that means that your denominator comes first, then your coefficient, your constant last, all right? And then there you go. That is factored, right? For that one, that would be the factoring. And x originally stood for sine, so all we have to do, we have our original GCF. And then we'll have sine minus 3 and 2 times sine plus 1. All right? That's as crazy as substitutions need to get. If it really just looks weird to be factoring with sines and cosines, treat them as you would x's and y's, right? And then go through it and turn them back at the end if you need to, right? That is totally factored. There's no squares left. Nothing more you could do there. Okay. Now, as crazy as it gets would be something with fraction arithmetic. Now remember, if your goal is fraction plus fraction, what do you need to do to add 2 fractions? What needs to always be true? Common denominator, right? And remember, common denominators are separated by multiplication, meaning that subtraction does not separate the denominators out. Like, yes, they both have a 1. I don't care that it has a 1 because that addition subtraction gorilla glues that whole thing together. That is one piece. So is this a 1 minus sign? No, which means that it needs to be multiplied by 1 minus sign. And what you do to the bottom, you do to the top. Okay, same thing. These are gorilla glued together, right? As soon as you see addition or subtraction, it keeps those together, which means that this needs a 1 plus sign on the left fraction. Right? Now, don't forget about that adorable little negative. I'm just going to put it right in front of my cosine there so I don't forget it, right? And then you're good to go. So I'm going to rearrange this a little bit. We have negative cosine x times 1 plus sine x plus cosine times 1 minus sine x. Now, sometimes I have students who will get that far and then they're like, yay, common denominator, you can combine them. You can. They're all in one fraction. Your fraction is still there. That has not changed. Do not forget that denominator. So we have 1 plus sine of x and 1 minus sine of x on there, right? Now, your goal is to simplify the expression by condensing it into one fraction. We have the into one fraction is solid. We just need to simplify from here, right? So we're going to take this, distribute, all right? Take that, distribute, right? We can simplify, you can combine like terms, multiply and distribute. So we get negative cosine x minus sine x cosine x. I'm just going to put the sign first because it rolls off the tongue easier when I say it. That's the only reason. Right? Same thing, cosine times 1 is plus cosine x, and then cosine times negative sine is negative sine x cosine x. Your denominator of the fraction, yeah, that hasn't changed. It's still there. Write it down. Okay. Now, numerator, you'll notice a couple things happening. We have a negative and a positive of the same thing. That's 0. And then we have a negative and a negative sine x cosine x. Those are like terms, right? Same variable, same exponents, right? So that means that we have negative 2 sine x cosine x, okay? Over your denominator, 1 plus sine of x, 1 minus sine of x, right? Now that is simplified and you're good to go. And as far as algebra is concerned, that is simplified into one fraction. That would be considered a good answer to end that. Now, if, right, we just learned about them, if we wanted to use an identity and simplify this down further, you actually could, right? Let me say this again. As an algebra answer, that is completely and absolutely simplified, right? That is absolutely good to end that. The only thing you could add on to from there is if you wanted to do trig equations. So for example, all right, make that very clear. If you wanted to, you could distribute your denominator. So you get 1 minus sine squared x when you distribute those parentheses, combine like terms. Fun fact, this, using a Pythagorean identity, is actually going to simplify into cosine squared x. Because I'm going to quickly go over that on the side. If I have sine squared plus cosine squared equals 1, and if I subtract sine squared, right? So then you get cosine squared equals 1 minus sine squared, right? That substitution, 1 minus sine squared into cosine squared, that is a Pythagorean. And then from there, you'll notice that now we have a cosine over a cosine, and because that's multiplication, you can essentially cancel one of those with one of the cosines in the denominator, and you're left with negative 2 sine x over cosine x. Well, fun fact, That is your quotient identity. That is also known as tangent. Right? So yes, again, you can end here for algebra. That is simplified, but using Pythagorean identities, quotient identities, trig identities in general, you can simplify it. Right? So just as a heads up, both are totally possible, but there you absolutely go. That is everything trig algebra as well as fundamental identities. Thanks for watching.